Hey physics students, in this video I want to show you some really cool things and I hope give you an idea of where we get all of the different equations we use for universal gravitation and figuring all this stuff out about planets and space and satellites. And so I want to look at the law of gravitation in terms of Newton's second law. So let's see if I can spell that right. So law of gravitation, and we're going to look at the second law. So you remember Newton's second law is force equals mass times acceleration. Now it seems like a simple little formula. It seems like a simple little equation, like there's not much to it. But just about everything seems to come out of that. And so Newton, once he sort of isolated this equation, force equals mass times acceleration, he used that as the base for all his other equations, and most specifically all of his stuff relating to gravitation and planet movement and all that. So let's think about, in terms of gravitation, you're looking at like a body in space, say this is the sun, and something is revolving around it. So all of this is circular motion, right? It's the force here is going to be a force of centripetal, and that force of centripetal is going to equal a mass times the acceleration of centripetal. Same concept, except of course, you have a constant force, right? A constant force which is pulling an object around a circle. So you're continually having a force which is continually causing an acceleration toward the center of whatever it's being pulled around. So in this case, right, being pulled around the sun. But this works for satellites, for moons, for planets, for anything orbiting anything else in space, which is what we see all the time. So this force of centripetal equals the mass times the acceleration. All right, so the force of centripetal also equals, well, let's just sort of sidestep this a little bit, and let's talk about the acceleration of centripetal. So we know that acceleration of centripetal equals the velocity squared divided by the radius. So to actually solve for acceleration of centripetal, you would do velocity squared divided by radius, right? So if I was to take this and substitute it in here, I would get the force of centripetal equals the mass times the velocity squared divided by r. We also know the acceleration of centripetal, if you were to look at time going around this circle, because it's circular motion, we talked about this in previous chapters, the acceleration of centripetal equals 4 pi squared r divided by the period, the time it takes to go all the way around squared. So that the acceleration of centripetal also equals that. So the acceleration of centripetal equals both of these two things. So you could say that the force of centripetal equals the mass times the velocity squared divided by r, or you could say the force of centripetal equals the mass times 4 pi squared r divided by time squared. So you could say that as well. So all of this, now make sure that you realize that all of what we just wrote here is essentially just this. We still haven't diverged from the same simple equation. We've just unpacked a little bit of what is included in this force equals mass times acceleration as it applies to circular motion of planets going around a body in space. All right, so here's acceleration of centripetal. Here's force of centripetal. Now what can we do with that? All right, let's think about a planet. As a planet is going around, like a sun or a satellite is going around a planet or a moon is going around a planet, we found that in his whole pursuit of trying to understand this, he decided that gravity equals mass 1 times mass 2. This is the formula for the universal universal law of gravitation, right? And so this is G for that universal gravitation number, which is 6.67 times 10 to the negative 11th. But this is a force of gravitation. Well, the force of gravitation is the force that holds the planet going around the other body in space. So the force of gravitation, this force right here, equals the force of centripetal, you see. So that means that the force of centripetal also equals the gravitational constant right here. M2 divided by the radius squared. So these are equivalent. So if you take that and you start to mess around with that a little bit, like what if we just look at these two equations right here? So let's look at these two equations. Let's take out that force of centripetal equals. So we know that these two are equivalent to each other. What we can do with this is we can actually take and we can isolate time, which is period. So we could solve for the period of any planet going around another body. Now you need to remember that all of this right here that we've just kind of brought out is essentially just still this equation, force equals mass times acceleration. So let's go ahead and do that. So what I'm going to do is I'm going to take t squared over here and multiply it by the other side. So that's going to get rid of that over here. And then I'm going to go ahead and multiply this side by the reciprocal of this. So I've got m1 m2, and then I've got r squared over here. So what's that going to equal? R squared times r is going to give me r cubed. Now what about the masses here? So in this particular formula, the mass right here is just the mass of the object right here, and then this one, and this is also the mass of the object, let's say. So let's say that m1 is the mass of the object and m2 is the mass of the central body. So you have a central body here, and this is the one that is being orbited around, and let's call this a satellite, okay? So satellites can be a lot of things. So why don't we just change this to S? So we'll change this to sort of help, and change that to C. So so down here, this is going to be S, right? And so we have S, and we have central body C. So if you look at that right here, we can get rid of that, and that helps to sort of clarify what we're working with right here. So we can get rid of that. So let's go ahead and see what we have. So we have 4 pi squared r cubed divided by the mass of the central body equals, equals g times t squared. So that's where we're at so far. So now what are we going to do? Well, we're multiplying by g, so let's go ahead and divide this side by g. So we're going to bring g over here, get rid of it right there. So now the last thing we need to do is let's just take the square root of all of this, and then we've got it. Well, the square root of 4 pi squared is 2 pi, and then we'll leave the rest of this in the square root right there. We have r cubed divided by the gravitational constant times the mass of the central body equals the period. And so there you have the equation to solve for the period of any satellite going around a central body. So that could be Earth going around the sun. That could be a satellite going around Earth. That could be any of those things. So pretty cool. So pretty amazing stuff. And all of this, remember, this entire formula right here is actually just this. And so if you're a little bit confused on that, just remember, follow through. This is force of centripetal. We just took apart the acceleration of centripetal into its parts, and we put it right there, and we figured out that it was equivalent to that, set them equivalent to each other, and figured out then that we could isolate for time. So we have all of these factors in here. We have distance from from each other. We have the universal gravitational constant. We have the mass of each thing, and we have the time it takes to go around it. So all we did right here is we isolated for time. So in the next video, what I'm going to do is I'm going to show how the second law, force equals mass times acceleration, can be used to solve for the velocity of a satellite. So I just showed you how you could use this to actually figure out the time of any satellite going around a central body. But you can also use this to figure out the velocity of any satellite going around a central body. And it still is just force equals mass times acceleration. So stay tuned to that next one, because that also is very helpful.